So far, except for a few examples, we have learned only about how to do LSH for Jacquard similarity using min-hashing. There are many other notions of similarity or distance, and which one to use depends on what type of data we have and what our notion of similar is. We're going to begin by studying distance measures in general and see the most useful measures. Then we'll talk about locality-sensitive families of hash functions as a general idea. We'll see that it is possible to combine hash functions from a family to get the S-curve effect that we saw for LSH applied to min-hash matrices. In fact, the construction is essentially the same for any LSH family, and we'll conclude this unit by seeing some particular LSH families and how they work for the cosine distance and Euclidean distance. We'll begin by introducing the distance measures we need, and we start with the formal notion of a distance measure. A distance between points in some abstract space is intended to measure closeness or similarity of the points. The lower the distance, the closer the points, and the more similar they are. Notice that Jacquard similarity is the opposite of what we mean by distance. Jacquard similarity is higher for similar sets than for dissimilar sets, while a distance measure would have their distance be lower. It turns out that 1 minus the Jacquard similarity is a suitable distance measure. To start, we see two different kinds of distance measures, Euclidean and non-Euclidean. Euclidean spaces have dimensions, and a real number locates each point along each dimension. The ordinary 2- or 3-dimensional Euclidean spaces are the most common examples, but Euclidean spaces can have any number of dimensions. For example, a 1-dimensional Euclidean space is a straight line infinite in both directions. An important property of Euclidean spaces is that they are dense. That is, given any 2 points, you can find their average, and it will be a point in the space. We'll see some examples shortly where there is no reasonable notion of the average of points in a space. That can be a problem in certain situations. For example, if you're trying to cluster points and you want to represent a cluster by a single typical point, it's nice to be able to take the average of the points in the cluster. But you can't always do that for non-Euclidean spaces. There are many notions of distance between points in a Euclidean space. The best known one is often referred to as the Euclidean distance, where you sum the squares of the distances between the points along each dimension, and then take the square root of the sum. However, we shall see that there are many different distance measures that also work for any Euclidean space. We shall often refer to any of these as a Euclidean distance. So what about other spaces and other distance measures? There are many of these as well, but a non-Euclidean distance is based on something other than the location of points in a space. A distance measure is a function from pairs of points to in some space to real numbers. This function has to satisfy 4 important properties. First, it never has a negative value, although the value can be 0. But the value of a distance measure can be 0 under only one condition, that the 2 points to which it is applied are actually the same point. Moreover, whenever applied to the same point, x as both arguments, the value must be 0. The distance is symmetric. That is, the distance from x to y is the same as the distance from y to x. And most importantly, the function must satisfy the triangle inequality. That is, the distance from x to y cannot be greater than the sum of the distance going first from x to some other point z, and then from z to y. We often see this idea in the observation that one side of a triangle cannot be longer than the sum of the lengths of the other 2 sides. The most common Euclidean distance is the L2 norm, which is the square root of the sum of the squares of the distances between the 2 points x and y, measured in each dimension. Another common choice for Euclidean distance is the L1 norm, or Manhattan distance. If you've ever visited Manhattan in New York, you know that the streets are laid out in a grid. You can't walk directly between points, and you need to first walk in one direction or dimension, say north-south, and then in the other direction, say east-west. As a result, the L1 norm between points x and y is the sum of the distances between x and y along each dimension. Here's an example of 2 points, A and B, in the two-dimensional Euclidean space. A is the point 5, 5, and B is 9, 8. The difference between A and B in the horizontal dimension is 4, and in the vertical direction it is 3. Thus, the L1 norm or Manhattan distance between A and B is 4 plus 3, which is 7. On the other hand, the L2 norm is computed as follows. We take the square of the distances 4 and 3 in each dimension, square them, and sum them. That's that. And finally, we take the square root. Since 4 squared is 16, 3 squared is 9, the sum is 25. The square root of that is 5. Here's another interesting Euclidean distance measure called the L infinity norm. Here the distance between 2 points x and y is the largest of the distance between x and y in any of the dimensions of the space. In fact, we can define the L sub r norm for any real number r. You compute this norm by taking the sum of the rth powers of the differences of the 2 points along each of the dimensions, and then taking the rth root of the sum. Notice that this definition is consistent with the definitions we gave for r equals 1 and r equals 2 before, and it's also consistent with the notion of an L infinity norm, because as r gets larger and larger, raising numbers to the rth power causes the largest of them to dominate the sum, and all other rth powers become negligible. Then, when you take the rth root of the sum, you essentially are taking the rth root of the rth power of the largest, which gives you back essentially just the largest of the differences. Now let's introduce the cast of characters for the non-Euclidean distances. First, the Jacquard distance, as we mentioned, is just 1 minus the Jacquard similarity. We have to use 1 minus, so identical sets have distance 0, and sets with no intersection have distance 1, which in this case is the greatest possible distance. And in this corner, the cosine distance. This distance requires points to be vectors. If the vectors have real numbers as components, then they are essentially points in a Euclidean space. But the vectors could, say, have integer components, in which case the space is not Euclidean. But either way, the cosine distance is the angle between the vectors. It's called the cosine distance because, as we shall see, it is generally easiest to compute the cosine of the angle between the vectors and then use the cosine to figure out the actual angle. The edit distance applies to points that are character strings. The edit distance between 2 strings is the minimum number of inserts and deletes needed to transform one of the strings into the other. There are some other notions of edit distance as well. For example, sometimes we allow a mutation as one edit, where a mutation changes one character to another. For example, ABC could become ADC in one edit. Without mutations, we would have to make 2 edits to make this change. First, we would delete the old character B, and then second, insert the new character D. So we would go A to B, C to A, C, and then finally to ADC in 2 steps. By the way, we're only going to talk about the insert-delete version of edit distance in this course. Finally, consider the Hamming distance. It's named after Richard Hamming, who happens to be the 3rd winner of the Turing Award, and it applies to points that are bit vectors of the same length. The Hamming distance between 2 bit vectors is the number of positions in which they differ. Here's an example of Jacquard distance. Consider these 2 sets, x and y. Their intersection has 2 members, 1 and 3. And their union has 5 members, the numbers 1 through 5. Thus, their Jacquard similarity is 2/5. But we don't want Jacquard similarity anymore. Now we want Jacquard distance. That's 1 minus the 2/5, giving us a Jacquard distance of 3/5. So let's check the 4 conditions for a distance measure. Jacquard distance is never less than 0 because the Jacquard similarity can't be greater than 1. The reason for that is that the size of the intersection of 2 sets is never greater than the size of their union. Now, The distance between a set X and itself is 0. Why? Well, X intersect X is the same as X union X, and both are X itself. So the Jacquard similarity of a set with itself is 1. Therefore, the Jacquard distance is 1 minus 1 is 0. We also have to check that if X is not equal to Y, then their Jacquard distance is strictly greater than 0. That is because if X and Y are different, then there's at least one element in their union that's not in their intersection, and therefore the intersection is strictly smaller than their union. That means the Jacquard similarity is strictly less than 1, and their Jacquard distance is strictly greater than 0. The symmetry condition follows from the fact that the union and intersection are both symmetric. That is, X intersect Y equals Y intersect X, so both intersections surely have the same size, and likewise for the unions. The last thing to prove is the triangle inequality. That's a bit of work, but we'll show the proof on the next slide. Here's the inequality that says the Jacquard distance from X to Z plus the Jacquard distance from Z to Y is equal to or greater than the Jacquard distance from X to Y. That is, this is the Jacquard similarity of X and Z, the size of their intersection divided by the size of their union. So this is the Jacquard distance from X to Z. And similarly, this is the Jacquard distance from Y to Z, and this is the Jacquard distance from X to Y. Remember, we proved that the Jacquard similarity between sets A and B is the probability that the min-hash values of A and B are the same. Or put another way, this is the probability that the min-hash of A and B are different. But the probability that min-hash of X and Y differ cannot be greater than the probability that the min-hash of X and Z differ, plus the probability that min-hash of Y and Z differ. By what we saw on the previous slide, this claim is equivalent to the triangle inequality. Okay. But the reason is that whenever the min-hash of X and Y are different, it is impossible for both min-hash of X to equal min-hash of Z and for min-hash of Z to equal min-hash of Y, because then by transitivity of equals, min-hash of X would equal min-hash of Y. So in terms of Venn diagrams, let the plane represent triples of sets X, Y, and Z. Here are those triples where min-hash values of X and Z differ. And here are the triples where the min-hashes of Y and Z differ. And contained within their union must be the set of triples where X and Y have different min-hash values. Another important distance measure is the cosine distance. Okay, this distance is useful for data that is in the form of a vector. Often the vector is in very high dimensions. For example, documents are often viewed as the vector of counts of each of the words appearing in the document, so each word is a dimension. Now, to define the cosine distance, think of a data point as a vector from the origin in some space to the point in question. Any 2 points have an angle formed at their origin between their vectors. Okay, so you have something like this. We can compute the cosine of this angle from the components of the 2 vectors. To do so, we take the dot product of the vectors. The dot product is the sum of the products of the corresponding components. And then we divide by the lengths of the 2 vectors. The length of a vector from the origin is actually the normal Euclidean distance, what we call the L2 norm, of the point at the head of the vector to the origin. That is, it is the square root of the sum of the squares of the components of the vector. For example, here are 2 vectors, P1 and P2. The dot product of the vectors is 2. The products of each of the first 3 components is 0. That is, 0 times 1 is 0, 0 times 0 is 0, 1 times 0 is also 0. But in the last 2 components, each vector is 1. So the dot product is the sum of 1 times 1 plus 1 times 1, and that's 2. For the lengths of the vector, P1 has 3 1s, so we sum 3 1s squared, and then take the square root, giving us the square root of 3. P2 also has 3 1s and 2 zeros as components, so its length is the same square root of 3. Thus, the cosine of the angle between P1 and P2 is 2, the dot product, that is divided by the product of the two vector lengths. Each of those lengths is the square root of 3, so their product is 3, and the cosine of the angle is 2/3. If you look that up in a table of cosines, you'll find that this angle is about 48 degrees. So here's a diagram with the two vectors P1 and P2 shown in the plane that passes through them. No matter how many dimensions the vectors have, any two lines that intersect, and P1 and P2 do intersect at the origin, they'll form a plane. I'm not going to do the math, but if you project P1 onto P2, as we have done here, the length of the projection is the dot product divided by the length of P2. Then the cosine of the angle between them is the ratio of adjacent over hypotenuse, which is the dot product divided by P2, that's the adjacent, and then divided by the length of P1, that's of course the hypotenuse. Let's see why the cosine distance satisfies the axioms of a distance. First, remember that vectors here are really directions, not magnitudes. So two vectors with the same direction and different magnitudes are really the same vector. Even a vector and its negation, the reverse of the vector, are to be thought of as the same vector. First, the distance between a vector and itself is 0. The angle a vector makes with itself is 0 degrees. Moreover, the angle of a vector with any different vector is not 0 degrees, so no pair of different vectors have a distance of 0. Again, remember, we think of vectors as direction only. Otherwise, you could have, say, a vector and twice that vector being, quote, different, and yet having a 0 angle between them. To make sure that all distances are non-negative, we shall interpret all angles as in the range 0 to 100 and 180 degrees. Notice that any two vectors from the origin will make an angle between 0 and 180 degrees in the plane they define. The rest of the argument is by physical reasoning. Symmetry simply says that the angle from vector to x rotating to y is the same as the angle from y rotating to x. And the triangle inequality is merely the observation that if we rotate from x to z and then from z to y, the total rotation can't be less than what we get if we rotate from x to y directly. Now consider the edit distance. Recall this distance measure assumes points are character strings, and the edit distance from x to y is the minimum number of inserts and deletes needed to turn x into y. There is an equivalent formula for edit distance based on the notion of a longest common subsequence of two strings x and y. The LCS of x and y is the longest string that is a subsequence of both. We say one string is a subsequence of another if we can get the first by deleting 0 or more positions from the second. Note that the positions of the deleted characters do not have to be consecutive. We'll give an example on the next slide to make these ideas clear. The formula for the edit distance in terms of the LCS is this. It's the sum of the lengths of the two strings, length of x, length of y, minus twice the length of the LCS. Here's an example where we'll compute the edit distance of these two strings x and y in two different ways. First, we can turn x into y by deleting a and then inserting u and v after the d. That uses 3 edits, and it's easy to check that there's no way to get from x to y using fewer edits. Thus, the edit distance is 3. Notice that we can get from y to x by doing the same edits in reverse. That is, we delete u and v, and then we insert a to get x. In general, a pair of strings can have several different LCSs of the same length. In this case, there's only one, B, C, D, E. It is obtained from x by deleting the first position containing a, and it is obtained from y by deleting the fourth and fifth positions containing u and v. And to verify that the formula relating edit distance to the LCS holds in this case, the sum of the lengths of the two strings is 5 plus 6, or 11, and the LCS has a length of 4. But 11 minus twice 4 is 3, which is indeed the edit distance. We can check that edit distance also satisfies the requirements to be considered a distance measure. First of all, the edit distance from a string x to itself is surely 0 because 0 edits suffice. Moreover, if x and y are different, at least one edit is required to change one to the other, so no other distances are 0. And there's no way for there to be a negative number of edits, so surely there are no negative edit distances. Symmetry holds because given any sequence of inserts and deletes, say taking string x to string y, we can reverse that sequence and replace the deletion of a character c by the insertion of c, and replace the insertion of c by a deletion. We saw an example of this transformation on the previous slide. And the triangle inequality holds for the following reason. One way to transform x to y is first to transform x to z and then z to y. The minimum number of edits needed to make those transformations is the sum of the edit distances from x to z and from z to y. But this sequence of edits is one of the possible ways to transform x to y, so the total number of edits is at least the edit distance from x to y. And next on our list is the Hamming distance. Recall the Hamming distance is the number of positions in which two bit vectors of the same length differ. So for example, the Hamming distance between p1 and p2 is 2 because they differ in the third and fourth positions. That is, here there's 1, 0, there's 0, 1. Other than that, they are the same. The argument about why Hamming distance is also a distance measure is quite the same as what we've seen before. The Hamming distance between a string and itself is 0 because surely the string differs in 0 positions. On the other hand, the Hamming distance between different strings cannot be 0 because they differ in at least one position. And there can't be a negative Hamming distance because you can't talk about strings differing in a negative number of positions. Symmetry of Hamming distance follows from the notion that the relationship different from on bits is symmetric. That is, A is different from B if and only if B is different from A. And the triangle inequality argument is very much like what we saw for edit distance. One way to change bit string x to y by flipping bits is first to flip bits to turn x to z, and then flip bits to turn z to y. The sum of these two numbers of flips cannot be less than the number of bits you have to flip to turn x to y directly.